And the next presentation is from the project TERA6G, and we should have Luis Gonzalez Guerrero connected. So Luis, if you may start sharing.
Yes, I should be sharing now, right?
Yes, just a second.
Okay.
Yes, please go ahead.
You are seeing my slides, right?
Yes.
Okay. So, good afternoon, everybody. I'm Luis Gonzalez Guerrero. I'm an assistant teacher at Universidad Carlos III de Madrid. I'm presenting today on behalf of Guillermo Carpintero, who is the PI of this project, but he couldn't present because he's catching a flight right now. So I'm presenting on behalf of him and, of course, of all the TERA6G consortium. In TERA6G, we are developing terahertz transmitters and receivers. So this is hardware project. And this hardware is based on photonic integration, and it will enable 6G wireless networks with data rates of terabits per second using MIMO technology. So our consortium comprises 5 different countries, Spain, Greece, Germany, the Netherlands, and Finland. And we are a total of 12 different partners. Half of the partners are working in developing the hardware, and the other half is working in integrating that hardware into the network. We also have a partner that is doing the socioeconomics analysis. So let me first show the 2 use cases that we are envisaging in this project. One of them is the one that you have depicted here, which is point to multi-point cross-haul in mobile small cells densification scenarios. So with the evolution from 5G to 6G, and also the adoption of traffic-hungry services, this will require smaller cells working at higher frequencies, and these small cells will need to be deployed very close to existing microsites due to the reduced coverage associated to high frequencies. So the microsites will need to aggregate the data traffic from different small cells, and then they will need to direct it to the core network. So one possible solution for this is to do a direct deployment of optical fiber between the DU pool and the macro site. However, this might not be possible in certain situations, like dense urban scenarios, which digging a hole for a new fiber might not be cost efficient or time efficient or even possible. And in that case, deploying a wireless link with high throughput might be the only solution to build a multi-hop network like the one depicted here. And this is exactly our goal in the project. The goal is to enable these wireless links with high throughput, actually with the capacity of an optical fiber. And for that, we are using photonic integration technology, and we are developing chiplets that I will explain later. And these chiplets can be reconfigured to reach the data rates of terabits per second. So the main characteristics of the hardware that we are developing in this project is that it's agile. It can switch between different spectrum bands. It's also scalable, because so the more chips that you add into the hardware, the more data rate you can achieve, and that means that we can adapt to the network capacity requirements, and also is reconfigurable, meaning that it can be used not only for communication, which is the main purpose, but also for other applications like sensing. Apart from this use case scenario, we envisage another one which is also point to multi-point, but in an industrial scenario, also requiring high throughput. So if we look at in more detail at the TERA6G goals, we are developing, as I said, we are developing both millimeter and terahertz transmitter and receivers with optical beamforming functionality. And this hardware is able to transmit and send several beams at the same time. And for that, we are using hybrid photonic integration technology, which means that we are using different integration platforms. And the hardware is being developed according to the specification or to the requirements of the two use cases that I just mentioned. However, since we are developing only one hardware for the two use cases, we decided that this hardware should cover the minimum most demanding requirement from the two use cases scenario. So if we assume that there will be two remote nodes per central node, and that each remote node will have two channels, that gives a total number of channels of 4 per remote node. And that's the number of channels that that will be supported by the hardware that we are developing. In terms of the distance, the most demanding minimum requirement in this case is 30 meters for the cross-hole small cell. That's the distance we are targeting. In terms of data rate, we are targeting 100 gigabit per second per beam. And in the frequency range, we will try to cover all these frequency bands. The only limitation in terms of frequency coverage is the separation of the antenna elements, but the rest of the hardware should support an even broader range of frequencies. And in terms of the scan angle, the minimum should be plus minus 45. It's possible that very broad angles will not be able to support 100 gigabit per second, so there will be some dependency on the angle of the data rate. But we need to explore that once we start doing the demonstration. So with the hardware that we are developing, as I said, we are expecting to reach terabit per second data rates, but also we are planning to use the same hardware for channel sounding and radar ranging. Apart from this, we are designing network functions to integrate the hardware into existing end-to-end communication networks, and also we are developing methods and algorithms to maximize the efficiency of this hardware. So here in this slide, you have an overall, the overall architecture of the TERA6G system, including the transmitter and receiver here in the central part of the diagram, and also the integration of this hardware into the network. This diagram represents the link between the central node and the remote node, and it's the basics of the network integration demonstrator that we will build for the project. And for that demonstrator, we will use a baseband unit from ICOM, which is one of the partners of the project. And in this baseband unit, we will have two modems, each of them generating a signal with a bandwidth of 2 gigahertz, and then located at an intermediate frequency that can range from 9 gigahertz to 15 gigahertz. Within the project, we are also developing the controller that will enable us to implement the beamforming algorithms. This controller will control the voltage and current levels that will be injected into the actuators of the hardware. And the voltages and current sources are also being developed within the framework of the project. They are being developed by ICCS, which is located in Greece. So let me explain the hardware itself. So as I said, the core of our hardware is the chiplets. Chiplet is a photonic integrated chip which generates a single radio frequency, carrier frequency, that can go from 100 gigahertz to 322 gigahertz, so the three frequency bands that I mentioned before. even if we have a single RF carrier frequency, we can still have several beams. And actually, we can have as many beams as optical modulators we include in the chiplets. In the chiplets that we are developing, we have 4 modulators, so that means that we will be able to beam steer independently 4 different beams, 1 per optical modulator. The output of the modulators go to an optical beamforming network, and this optical beamforming network is responsible for directing its beams to a certain location. After that, so the optical beamforming network has 4 inputs in this case for each beam, and then it has as many outputs as antenna elements, which in our case is 16. So this is 4 inputs here and then 16 outputs here. And then the 2D antenna array will launch each beam into the free space. And then, as I said, these beams will have the same RF frequency, but they can be directed independently. They can be directed to different locations. A little bit about the integration technology that we are using. We are using 3 different platforms. Here in red is silicon nitride, which is the platform that we are using for the passive elements, such as the optical beamforming network and also the laser cavities. And for the active elements, we are using indium phosphide. So for the modulators, for the gain chips of the laser, and also for the amplifier array. And then we also use a polymer-based platform, which is here depicted in blue. And we are using this platform to do the routing from the optical beamforming network to the antenna array. And this platform, we can build 3D chips, 3-dimensional chips. And this is very useful because otherwise here we would have a lot of crossings, and those crossings would mean very high optical losses. With the 3D polyboard technology, we can avoid those losses and keep a high gain link. So in this project, we have 2 generations of hardware. The first generation will only have 1 chiplet. But for the second generation, we will include a second chiplet. And basically, this means that we will replicate this structure, and then we will combine the 2 of them with the 3D polyboard technology that I was mentioning. Since each chiplet can support 4 beams, that means that in the second generation, we will be able to generate 8 different beams, 4 with the same RF frequency, and the other 4 from this chiplet with the same RF frequency, but that can be beam steered independently. So a little bit more information about the antenna. So this project is building from the results of a previous project called TeraWay. In TeraWay, we developed 4x1 antenna arrays. The emitters were based on high-speed pin photodiodes, and on top of the photodiodes, we use a bow tie antenna. And then to extract the electromagnetic wave from the indium phosphide and launch it into the free space, we use rod antennas, as the one depicted here. And in order to hold the different rod antennas, we are using a technique called effective index, which is, if you look at here at this section, you will see holes here drilled in the silicon. In terms of the electromagnetic radiation, this behaves as air, so it doesn't mess with the electromagnetic wave that goes through the rod antenna. And that's how we can have different rod antennas all in a single piece. Here is the radiation pattern from a single rod antenna. As you can see, it's quite low gain, but that's required for beam steering. The maximum angle that you can achieve in beam steering is ultimately limited by your antenna. So if you want to beam steer over a broad range, you need to have a low gain antenna. And then, so the power from a single antenna is -8 dBm. And in order to increase the power, what we do is to combine the output from different antennas. And we measured the output power that we got from the 4x1 array, and it was -11.3 dBm. So that was for TeraWave. In this project, in the current project, we will have 16 elements. So this is an actual picture of developed chip for the project. And as you can see, we will have 16 elements, and that means that we should be able to increase this power at least by 6 dBs, which is multiplication by 4. And just to finish, the beam steering is enabled by the optical beamforming network, of course, which is implemented in the form of a blast matrix. Blast matrix is a matrix of phase shifters and Mach-Zehnder interferometers. And it has 4 inputs, as I said, 1 for each channel, and then it has as many outputs as antenna elements. So in this case, it has 4 inputs and 16 outputs. And that means that this matrix has a total of 4 times 16 pairs of phase shifters and Mach-Zehnder interferometers. So we need to have phase shifters and Mach-Zehnder interferometers because we need to control both the amplitude and the phase of the beam. And so the phase is controlled by the phase shifter and the amplitude by the Mach-Zehnder interferometers. In any case, as I was saying, this matrix contains 4 times 16 pairs of phase shifters and Mach-Zehnder interferometers, and its configuration is rather complex. But we are developing some algorithms to ease and facilitate the configuration of this blast matrix. So we will have fixed beams with a fixed position, and each beam will have certain weights in terms of the electrical signals that are required to generate them. And its weights, the weights associated to each beam, will be coded in something that we call code word. So a code word means or relates to a single beam, one code word for each beam, and all the code words are stored in a code book. And this code book, which is just representation of all the beams that we can generate, has different levels. In level 1, we activate only 2 elements of the array, and we generate two beams. So these beams have a fixed position, and in order to cover all the space, of course, these beams are quite wide. If we go to the second level, then we activate more elements in the antenna array, and then we generate more beams. And since we have more beams, they can be narrower, and they still cover all the space. If we go to level 3, then we will have more beams, but narrower beams. And then if we go to level 4, we have 16 different beams covering all the space. So this is everything from my side. If there are any questions, I don't know if I have much time to answer them. If not, I will try to answer them offline. Thank you very much.
Thank you very much, Luis. Very good presentation. I don't see actually questions on the chat. We have a minute. Is there any question for Luis? No. So we can probably go to the next presentation. That is from the project 6G tandem. And Lisbeth is already with us and ready to start sharing, I can see. So thanks a lot, Lisbeth.